Now we have not learned any concrete thing regarding how to decide a matrix is diagonalizable or not, therefore this theorem. Okay, so proof we will see in future, obviously if time permits. Okay, so let A be a real matrix of order and then following statements are equivalent. The first one is A is diagonalizable. The second one is R raised to n has a basis consisting of eigenvectors of A. So this point will be clear later on when we will see the examples. That the third one is algebraic multiplicity of eigenvalues should coincide. Coincide means equal. So algebraic multiplicity of each eigenvalue should be equal to its geometric multiplicity, and that is exactly what we are going to use in order to check given matrix is diagonalizable or not. Very important, I'll say very important point it is that we are going to use to show a matrix is diagonalizable. So what we will do is, given a matrix A, we will find all its eigenvalues. Once we get the eigenvalues of that, corresponding to each eigenvalue, we are going to find its algebraic multiplicity and geometric multiplicity. So if algebraic multiplicity of each eigenvalue is equal to its geometric multiplicity, then we will say that our matrix is diagonalizable, and we can find that non-singular matrix P also. Now since it is diagonalizable, it will be similar to a diagonal matrix, right? So therefore we can find that non-singular matrix P also, such that P inverse AP is equal to what? A diagonal matrix, and we will see while discussing the example. Okay, and the last one is sum of dimensions of eigenspaces of A is n. This is also very simple. Suppose your matrix is A and suppose the eigenvalues are 1 1 2. So how many eigenspaces are there? Eigenspaces are only 2, E of 1 and E of 2. Okay, and the dimensions of this eigenspaces, the addition of dimensions of these eigenspaces should be equal to n. N is the order of the matrix, so it should be equal to 3. So if it comes out to be equal to 3, then we can say that our matrix is diagonalizable. So it means that just remember one thing, it is always guaranteed that the dimension of your eigenspace is always greater equal 1. It will never happen that the dimension of the eigenspace is equal to 0. Remember, because eigenvectors are always non-zero, so dimension is at least going to be 1. Okay, so dimension of E of 2 will be at least 1, dimension of E of 1 will be at least 1. Okay, so if dimension of E of 2 is 1, then in order to say that A is diagonalizable, your dimension of E of 1 should be 2. Okay, because I want sum to be equal to 3. I hope you are getting my point. Okay, yes, and over here also I would like to clear one more thing. Now listen it properly. See, whenever the algebraic multiplicity of your eigenvalue is 1, right, and we are saying that geometric multiplicity is less equal algebraic multiplicity, is that okay? Now since I am saying that dimension of eigenspace is always greater equal 1, in other words I am saying that geometric multiplicity is always greater equal 1. Is that clear? So remember that geometric multiplicity of eigenvalue is always greater equal 1. Now whenever your algebraic multiplicity of eigenvalue is 1, in this case the algebraic multiplicity of, now instead of saying algebraic multiplicity, I will use short form, that is AM. Now since AM of eigenvalue 2 is 1 and we have the property that GM is always less equal AM, so therefore we can say GM for eigenvalue 2 I am talking about will be less equal 1. So GM is less equal 1 on one side and GM is greater equal 1 on the other side. So what should be GM? GM should be equal to 1. So my point is, if your algebraic multiplicity of the eigenvalue is 1, then in that case you are going to get geometric multiplicity to be 1. In other words, whatever eigenvector you are going to get corresponding to eigenvalue 2, in this case it is also going to be 1. Geometric multiplicity is 1. What is the meaning? The dimension of E of 2 is 1. Dimension of E of 2 is 1 means what? The basis set of E of 2 will contain one vector. So it means what? It means that the eigenvector corresponding to eigenvalue 2 is going to be only 1. Is the idea clear? So Therefore, I told you that if you are having all the eigenvalues distinct of a matrix A, then it means that algebraic multiplicity of each eigenvalue is 1. Whenever the algebraic multiplicity of each eigenvalue is 1, the geometric multiplicity is also 1, isn't it? So therefore GM will be equal to AM for each eigenvalue, and therefore your matrix will be diagonalizable. Okay, so this is a beauty of the distinct eigenvalues concept. Okay, and you should note one more thing. If the eigenvalues of certain matrix are distinct, if order of the matrix A is 3 and if all the 3 eigenvalues are distinct, then note that corresponding to each eigenvalue you are going to have one eigenvector. So corresponding to eigenvalue 1 you will have one eigenvector, corresponding to eigenvalue 2 also you will have one eigenvector, and corresponding to eigenvalue 3 also you will have one eigenvector. Then the question is, when the eigenvectors will be 2 corresponding to some eigenvalue, that depends on the repetition. If your eigenvalues are 1, 1, 2, then it may happen that now since the eigenvalues are 1, 1, 2, I am assuming that order of the matrix is 3, the eigenvector corresponding to eigenvalue 2 is going to be 1, but the eigenvector corresponding to eigenvalue 1, in this case it may be 1 or it may be 2, we are not sure, but remember that it is always going to be either 1 or 2. What is the reason? Because GM is always less equal AM. Whenever we talk about GM, it means the eigenvectors only, the number of linearly independent eigenvectors. Is that okay? So therefore, whenever the algebraic multiplicity of certain eigenvalue is 2 in this case, then your geometric multiplicity is going to be less equal to, in other words, it is either going to be 1 or it is either going to be 2. So number of eigenvectors will be either 1 or either 2. It depends on the example. I hope this idea has also been cleared. So I have explained a lot of things in this lecture. So now still if you are having any doubts, definitely you can call me. So now I think we are ready to go for some examples of what? Diagonalization.